It's nice when you are the last one to talk because I threw away 10 slides. So thanks to Zecchina for giving the fundamentals of machine learning, and many things have already introduced the topic. So let me put things like this. We've been in the business for 30 years now, basically. So together with a few other people, we established the field of astroinformatics. We are basically George Orgowski, Alex Delay, and is my voice, which is subsonic, and established this new field in astroinformatics in the 2000, I would say 2005. Since then, there has been an explosion of application of machine learning astrophysics. Here you see a few proceedings over the last few years. And I'm afraid that we are still far away from understanding what we can do with this tool. Also because it's the traditional justification for machine learning in astrophysics is that you have modern instrumented detector which produce zillions of data, and this data cannot be processed with the traditional methods, right? So, I mean, you've heard some applications today. If you open the journals, you find hundreds of different applications, but the problem is always the same. You want to use a supervised or unsupervised method to perform traditional tasks like photometric redshift, like extraction of patterns from images and so on. And this is basically a result of an historical process, which you can see there. I mean, machine learning is a new thing. Old professors like me, I'm an exception because I was interested in this at the beginning. But basically in astrophysics, know nothing about machine learning, absolutely. They just hear from a colleague that machine learning is interesting, and therefore, please find a smart student who is faster in learning, more brilliant, and so on, and give him an old-fashioned problem to solve. Obviously, the student who has no formal training in statistical learning or in mathematics for machine learning or in machine learning itself, since it is easy to download the stuff from GitHub, Colab, other repository, and this type of things, get a deep learning algorithm, implements it, usually, unless you are completely stupid, the algorithm performs like the old professor or even better, because these algorithms are very complex. They can deal with the problems easily. So the final result is that at the end of the process, the professor is happy because basically his intuition was right. The student publishes a paper, and usually that paper means nothing. I mean, you can ask two people who referee works in this field. If they are refereed by an astronomer, usually they passed after the second trial because the astronomer gives up on the machine learning side. If they end up in the hands of a machine learning guy, they are rejected 70% of the time because they are not sound, they are not statistically sound. They basically make no sense from the point of view of machine learning. Therefore, it's not an easy task. This is the main point which I want to do to the end of this point. If you believe that you just take off the shelf a piece of software, use TensorFlow, and get a fine result, you're living in a different world. It doesn't work like that. So, but there is a more important thing for us, and this is where I think to make a few conversions along the road. This is not why I entered this field 20 years ago, Massimo entered this field 20 years ago. I'm not interested in data science. This is a complex for cosmologists who need huge statistics, you know, to put a problem. I'm interested in what machine learning can do about complexity. Machine learning offers us for the first time the possibility to explore the huge, complex, observed parameter space which come out of modern data in astrophysics. What does it mean? Well, very simple thing. Sorry, wrong direction. Remember that all physics law come out from empirical laws. These empirical laws come out of trends in data. There is a fantastic book And basically, theory, I'm sorry for theoretical physics, from the information science point of view, are just compression algorithms, which allow you with a few free parameters to remember a huge variety of phenomena, to describe a huge variety of phenomena, okay? So, read this paper, The Growth of Astrophysical Understanding. It's an old paper, New Scientist, by Martin Arwitt, a cosmologist, who basically explains you how the whole history of astronomical discovery is somehow related to a better exploration, to a better sampling of the observed parameter space. Each measurement you make, it's a point in this very high dimensional parameter space. Right ascension, one dimension, declination, another ascension, epoch, another ascension, flux in a given band, another dimension. If you put together all, you realize that, for instance, a point in the Sloan digital sky survey is defined in a space of 330 dimensions. If you put together Sloan with Euclids, you end up at 600 dimensions. If you put together multi-wavelength observation of galaxies, you end up at 1,000 dimensions. And there you are stuck with what you do. We have always done like this. Let's use a machine to do the same. And this is suicidal. Just a simple question. Do you know any physical law? This is a starting point, actually, which depends on more than 2 or at most 3 independent variables. I have asked this question for the last 20 years. No one was ever able to answer, one exception, the standard model of particle physics. That's the only exception. Do we live in a simple universe? Or rather, it's just a result of human biases. Our brain is incapable to perceive pattern in more than 3 dimensions. You trust your brain. Look at this image. What is in there? The classifier, the network in your brain, the classifier network, which has been trained since birth, has never been trained to recognize this. You turn it by 180 degrees, and you recognize that there is a deer. Your brain defines the limit of our knowledge, and what is more important, defines also type of problem which we are asking machines. This is what I mean with complexity. I hope that a new generation of the data scientists or machine learning of teams, basically, and we will get to this to the end. Either you are an astrophysicist or you are a data scientist. Hybrid does not exist. You have 2,000 professional publications in astrophysics, 2,000 increasing professional publication in machine learning. You cannot be proficient in both of them. So either you suck at one thing or you suck at the other thing. No way. You need to be in teams with very specialized competencies. Okay. Well, you already have seen this one with Zekina. All neural networks, deep learning, whatever you want, are just universal function approximator. That's it. You just are solving an optimization problem where your variables are the weight, and you want to find a minimum number of features to represent your phenomenon. So, the idea is beginning to work. I want to give you a simple example of what I'm doing. How many of you in the room are astrophysicists, so that I save time for the presentation? Very few. So most of you don't know what photometric redshift are. They have been mentioned, okay? They are crucial. You use them to measure the distance of galaxies. Whatever it does will not work without photometric redshift, basically, because if you don't know where the galaxies are, you go home and that's it. You can do it spectroscopically. It takes a huge amount of time. You want to do it with the photometry. In one night, with a good telescope, you can get the spectra for 200,000 objects. So basically, it's an inverse problem. You want to use photometry and to map the photometric space into the target space, which in this case is a spectroscopic redshift. Okay, very simple. it's 20 years that the two of us are working on this problem, which is simple and still poses a lot of, okay. But let me show you what I mean with complexity. This thing here is very simple. It's a brute force approach. Since the old professor had told that photometric redshift had to be derived from those set of parameters, no? The first experiments were done following the old approach. You have a set of galaxies for which you know the spectroscopic redshift. You have a huge number of objects for which you want to derive the photometric redshift. You train supervised a neural network on the spectroscopic sample, you predict the photometric redshift. And then you evaluate the performances on the test set, standard approach. Sloan provided 330 parameters, it's a survey. Among these, 55 were more meaningful. So if we use a traditional approach, which is one followed by Laurino et al., Brescia et al., Brescia is that guy over there, you get what humans following the traditional approach can get at the best. Up there, up there. What are these points? The results of an extensive simulation where a crazy guy at Heidelberg attempted the 340,000 experiment, different training and test on the same data set, picking up random combination of the parameter among the 55 which were selected by Sloan. Machine outperformed by a factor 2 humans. They find combinations of features which never a human expert would ever proposed. Never. Because data are not perfect. Noise cannot be simulated. There are leaks in the filters, whatever you want. At the end, you end up with the best combination of parameters found on a machine, which is this one, which doesn't make sense to an astronomer. These are quasars. Unresolved object in the Sloan. PSF, which means point spread function magnitude. The model magnitude should be the same. So basically, it's why, in some cases, you need a combination of PSF and the model. Because filters in the instrument can be misaligned. The astronomers will never realize the machine realized that. That creates a coma, an extended thing, which is detected by the instrument, for instance. But you can go further. Sloan gives you 330 parameters. Sorry? In a few cases after, basically we took this data, we sent them to Peter Kapak, who was in charge of the Sloan. Peter, by looking at this data, oh yes, there is that leak in that filter which can be responsible for that. And the other, we understood it was a misalignment in the filter, but wait, because here we cannot really understand anything. At that point, take the 330 parameter provided by Sloan. You cannot do all permutation because that would be the number of experiments at the age of the universe would not be enough from computing time, okay? It's 1 sextillion experiment. So you use a different strategy because you do most significant feature after most significant feature. And you end up with the 10 features which saturate the problem. So the traditional approach to the evaluation of photometric redshift is basically based on the experience with the human old professor, is undershooting. 4 parameters are not enough. They do not saturate the problem. The problem of photometric redshift can be solved only by 10 parameters. There you achieve a plateau. Different combination achieve that plateau of feature, but if you look at those, they don't make any sense to the astronomer. In fact, the subsequent step is to let the machine measure the parameters. And this is really a terrible strike for the astronomers. It's what you do when you feed the image directly instead of feeding the measured parameters, you know, because parameters are model dependent. The CERSIC is model dependent. The aperture magnitude is model dependent. There is always some input from the human, which takes information away from the data. Machine can do better. Let me show you two examples. I hope we have enough time to show both of you. One problem standard, I mean, it's not that people who work in this field do always the same thing. It's basically that if you want to work supervised, you have a few training sets. One is galaxy morphology, and the other one is photometric reddish. There are a few other cases where you have large enough data set. It's not that we are monotonous people. It's just, those are the template data set. This is what we do. Galaxy morphology is fundamental for cosmology. You can explain why, I don't waste time. It's for galaxy evolution, galaxy dynamics, galaxy formation, cosmological models, everything. And it's the most stupid thing because galaxy morphology, we all know, is biased, is based on human judgment, has a weak correlation with physical properties because that's the main point. Has no physical information. For instance, in galaxy morphology, there is not information on the presence of an active galactic nucleus, massive black hole in the center, okay? There is no information on whether that object has received a major. Actually, there is. Usually they place it as peculiar object, which doesn't make any sense. Well, it's also known that is a fantastic thing. People should read the literature. I'm sorry, but I must say this. In 1995, the first leading galaxy classifiers, human classifiers in the world, gathered together to see how coherent they could be. There is that beautiful paper. By comparing classification made by human classifiers, there is an error of 2 beans in galaxy morphology. Okay, and you find that people try to reproduce the human bias in classification morphology with accuracy higher than 1 bean. Come on, it's in the knowledge base, the 1.8 error in the classification. You cannot do better than that. When people succeed, it means that they are overfitting. Please. The microphone.
Sorry, can you repeat this point? Because I think I didn't got it, and it sounds important.
Yeah.
Can you repeat
Here
the point of this article? Like, because
Buta, Corwin, De Vauclair, Dressler, Vandenberg, and Story Lombardi were the people who have compiled the catalogs of morphological types of galaxies done by visual inspection, which is at the basis of visual inspection. The same data set was put under scrutiny of these 6 experts, and then the classification were compared. There is an error of 1.8 beans average in the classification. So even humans, the world expert in the field, those who have, I mean, De Vauclair established the classification scheme to give you an idea, okay? Buta invented the ring galaxies. I mean, these are really the masters. Even them could not agree at better than 2 beans. In this classification here, sorry, 1 step in this direction is 1 bean. Okay, this is more or less a classification scheme. So basically, the difference between an SGD galaxies and SCD galaxies is within the errors. Yeah, okay. This is sorry, my mistake. This is the Hubble classification scheme revised, basically, but it is the. Okay, so literature is full of attempts to reproduce galaxy classification with machine learning. I am impressed when I see people who achieve an accuracy better than 1 bean, which really means that they are perfectly reproducing the human bias. And they claim to do science out of this. Okay. I don't want to be hypercritical, but I mean, knowing the literature could help a lot. Okay, so, but you can change approach. This is a very nice idea. I mean, I have a different approach with so I just pick up the right people. I have very little to do with what I am going to describe. These are my PhD students. They are orders of magnitude better than me. I'm not kidding. It's not false modesty. And therefore, Lars Dorenbos, Stefan Pavluti, and Olena Torbaniuk are are the people who really did the work, but this is a very simple idea. Galaxy morphology, this just is coming out. This has just been accepted. We have a problem finding AGN from photometric image. Professor Marconi can tell you how difficult it is from a single image. From 3 bands, 3 images in 3 different bands, it's difficult. From a single image, it's basically impossible if you follow the traditional procedure. So, fantastic. You don't need every time to retrain a network. This is a fixation. And if ImageNet is capable to recognize muffins from puppies, well, it means that all features which are relevant for the world are in that data set. So just don't waste computer time. Take a pre-trained ImageNet, the one which is used by Google to classify, everything, and shovel in it a catalog of images or galaxies using the pre-trained features. Each galaxy will be decomposed in its main feature and then work on the feature space. Since you are computer scientists, I don't waste time. Basically, you have, the sort of, network. You reduce the dimensionality until you go to the core where you have a limited number of features. Okay, you take the pre-trained feature of image. Then you have your galaxies, basically the whole data set of the kids survey, to give you an idea, 300,000 galaxies, which have been represented in this feature and work in the feature space. There is where the information is. So for instance, in our case, we took AGN galaxies with active galactic nuclei and galaxies without active galactic nuclei, classified on the basis of BDP diagram, basically on the product. And we went to look for objects similar to those ones. So basically, we have a set of prototypes, and we go to the field. We take the prototype is a point in this 1024 dimension parameter space. We look for the objects around it. Simple metric distance, nothing complex. You don't need to make a. And you find the objects which are very close to it. And then you use your knowledge to evaluate whether the method works or not. Look, it's impressive. I mean, that is the second prototype, third prototype, 7th prototype. Here you see, you have a bright spot, you get all objects with the bright spot. So you must be careful in this. You must select the right set of prototypes. And you end up with the results like this one. Okay, this is a composition of our data set. Let me show you the results here. You rank the objects in order of distance from your prototype, and you find that there is a huge improvement with respect to traditional techniques. You have, for instance, that among the first 25 objects, closest neighbor, in some cases, 60% of the objects are AGN. And this is already something which, from image, without spectroscopic information, from image in one band, was never done before. No effort. The tool was there. You just need to start thinking orthogonally to what your professor tells you. We do science in the old way. This is a new word. You must understand the methods, and you must use the methods for what they are, not for what I think they are. Let me show you something. Then you can do something smarter. This was an idea by Stefan. You have that objects are losing coherence after the 25th object. So why don't we do it in a recursive way? The first one is a 61% probability, for instance, to be an AGN. So I redo the ranking, but on the second one, and they take the object which is the closest to the other one. Because the closer you are to the prototype, the more likely you are an AGN. You do it in a recursive way, and you end up with this, up to 70%. So basically, now from the kid's image, using just a small sample of AGN, we can tell you with 70% accuracy which galaxies contain an AGN and which galaxies do not contain an AGN. It works well even in one band. You can see in this previous slide here that is in G band, photometric band, R band, I band, and with all three bands. Look at it. You have a fantastic correlation. No spectroscopic information used. No BTP, nothing. Obviously, you need to have a good prototype. No training time needed. You take ImageNet, which is already trained. Easy. Okay, I leave time for second things. Different project, different students. Michele Veneri, in a few seconds you will see a nice picture of him. The very bad problem, 5 minutes. ALMA, radio interferometry, same problems which the community will encounter with the square kilometer array, data cubes. Is in radio, so you have bidimensional images stacked in frequency, and these stacks can consist of 6,000 up to 16,000 channels, depending on the instruments and so on. And you want to find objects in them. The point spread function, the impulsive response of the instrument is not circular, is not symmetric, depends on the position, on the orientation, on everything. It's quite a complex problem. This was accepted, I think 2 days ago. It will come out on monthly notices. It's a new tool to extract the source. That is Michele after finishing the work in 3 years of not sleeping, so it's perfectly understandable. He did an immense amount of work. And you can do it with a different approach here, exploiting deep learning to its best. Lack of training data, so therefore we had to rely on simulation. These simulations are quite reliable because, you know, in the radio it's easier to simulate objects because you have very good mathematical models of the instrument, you have basically point sources. Okay, so we had to first do the simulation, then to check that the simulation were populating the parameter space in the proper way. These are tests, I'm not going to waste time. And this was a final pipeline. 3 different pipelines of deep learning chained one into each other, each one doing a different job. The first one is basically convolutional autoencoder, which does the source extraction. So basically recognizes the presence of objects in the data cubes and then identifies bounding box in the data cube, these red squares here, which are used by the instrument to do the spectral focusing in the 3rd dimension and the blending. We were mentioning before the blending. And I'm not going into the detail, but if you wish, I can give you the preprint. These are the results of your first row original data, second reconstructed, the 3rd bounding box. Then you have this bounding box. They're passed to a deep GRU gated recurrent unit network, which does the focusing in the 3rd dimension in the spectrum, identifies the presence of the peaks. If there are 2 peaks, basically, it means that the object is blended in the image plane and therefore is moving. You have to find this information in the 3rd dimension, the spectral dimension, and then it flags it for the blending. Finally, once you have defined the bounding box, the blended the object, you feed it to a battery of ResNet. Each one of them is performing the measurement of a specific parameter. In this case, we need to measure what a radio astronomer wants, which is inclination, flux, and this type of things. Okay. Very quickly, this is a typical example. Reference dirt integrated group. spectrally focused, that they are blended, that this is a result of the blending, this is what you get at the end. Results compared to all, and here, Alessandro, you can tell me, these are the results compared to Decoras, which is the only other pipeline, deep learning pipeline for the same task, with the Sophia 2, which is a standard. Yeah, I'm finished. This last slide. And as you can see, this pipeline, fine-tuned 3 years to write, outperforms all the others in all indicators. I'm not going to show you this because these are just confirmation of what I'm saying. Conclusion. Okay, machine learning offers us a concrete possibility to expand our knowledge, not to confirm what we already know or to do better what we already know. But feature selection and feature interpretation are one of the most important parts of the story, and they are very seldom treated, even in specialized journals. I don't take even in consideration a paper where there is no discussion of a feature, of the features which you extract, because there is where the physics is, there is where the information is. Better use of simulations is crucial to exploit these tools, but we can discuss this another time. It is not a one-man job. You cannot be a real professional in machine learning and a real professional in astronomy simultaneously. This is what astroinformatics is all about. You have astronomers, you learn to speak with a computer scientist or with a statistician, people who are experts in machine learning, and people from those other two worlds, which understand how to speak with the astronomers. You're young, full of enthusiasm, but trust the experience of someone who has been for a long time in this field. If you dream to be professional in both, forget it. You are not Einstein. I'm not Einstein. No one is Einstein. The amount of material which you must process in the two fields is beyond human capabilities. You can become a practitioner, but you will never understand really what you do, either in one field or the other. So choose on which side of the problem you want to be. This is the first choice you must do. Okay, I'm done. So if you have a question, I'd be happy to answer.
Thank you, Giuseppe.
Thank you.
Questions? Before we start, I have a question.
Yeah.
Maybe I don't know if I understood correctly when you describe the identification of the AGNs, active galactic nuclei. So basically, you take a pre-trained network trained on other kind of images, completely different, and you use that to identify the features of each image.
Basically, you transform, let me put it again, you compress that image using the pre-trained ImageNet to the space of the feature of ImageNet.
And then you identify a few
objects for which I know. Yeah, exactly.
And then you find those which have the similar features.
No, then I find where they project in this parameter space. And with the metric distance, I start measuring in order of distance from that prototype. The simplest thing in the world. Once you have understood the trick, you can implement it in 10 minutes.
So you can do it for any kind of image.
Any kind of image, for instance, mergers, and also blended. Where is that? The lady who gave that beautiful presentation before. Blended galaxies. And this thing should work wonderfully for the simulation. You just run there, you identify, or even objects for which you know they are mergers. You just plug them in, see where they fall in the feature space. The nearest objects are very likely to be the same type of object. And so, I mean, we need also to simplify a little the life, you know. It's yeah, because I see people extracting features for barred spirals, for spiral galaxies. I mean, they are objects. A car is orders of magnitude more complex than the image of a galaxy. Your face is orders of magnitude more complex than the image of a galaxy. So if, well, with the mask, it goes through. But so basically, if these objects are capable to disentangle, because at the end that it is a phase, so it's a galaxy, it doesn't care anyone, it's in the interpretation that the problem becomes relevant. But from the point of view of vision, is relevant. If I can tell the difference between a car and an orangutan, I can also tell the difference between a elliptical galaxy. The only way is to do things properly.
So in practice, you do a training with an already trained network.
Exactly. I don't train anything, basically. I take the object, I threw them into...
So you see how a trained networks apply to a given example, and then you find...
I train basically on the image, but in the last stage of on the last layer of the machine. That's it. Yes.
Curiosity precisely with this nice thing that you showed. So, but what do we learn from this? The fact that, like, if I understood well, this outperforms categorization algorithms which are based only on the visible images, right? That's what you said.
Yeah.
So does this mean that in fact there is more physics in the visible?
Absolutely.
And so now you should look for it.
Of course, that's the idea. But the problem is that you run into problem when you try to teach machine to reproduce human biases. So you must set, and to define the problem on a more physical ground is not easy, because you need to decide whether to work on images, whether to work on tabular data extracted of the image. And then you need also to establish some criterion to establish a physical classification of galaxies. So basically presence or absence of AGN, Halo occupancy factor, mass, flux. And once you have that, yes, absolutely, you should completely ignore human bias and let the machine find the solution. And they, as a human, you must interpret whether the machine, went crazy or not. But in the past, it was just an attempt to reproduce. This was fantastic. I mean, the absolute stupidity. Galaxy Zoo was already done using algorithm machine learning based on the decision taken by humans. So basically, it was just a consensus on human decision processed through machine learning. Then you train machine learning algorithms to reproduce the output of a Galaxy Zoo. It's basically a vicious circle, which doesn't lead anywhere. But there are dozens of people who are doing that in literature, which makes no sense to me, at least. I mean, then, obviously. Yes, that's true, yeah. And also, to parameterize it. I mean, it's, so it's be more critical in comparison to how you are using machine learning. There are,
Okay. And item number 3 on your conclusions is to make better use of simulations.
Yeah.
So what do you have to do? I mean, it's a problem all of us have in whatever field. What do you have to do to make sure that your simulations are really good enough in order to obtain outstanding results?
you should not ask me. I am not you should ask Luca. Where is he? He went away. I mean, you need the simulation because modern instruments are pushing knowledge beyond the limits of what we know. So when you go into uncharted territories, like for instance, when you go beyond the spectroscopic limit, existing spectroscopic limit during photometry, and for instance, you are trying to derive photometric redshift of objects below the spectroscopic limit, you're in uncharted territory. So you need to have simulation to guide you in this process. But this simulation usually are done in a rather naive way, especially when we are trying to simulate the data. I mean, the experience we had in the past, when I say we, I mean massive perturbation myself. And in the past, that when you use machine learning on simulated data is one thing. When you use the same identical method on data, real data, you encounter a whole set of problems, which I think you can confirm on that. I mean, basically you encounter, which you could not model in your simulation and so on, like for instance, you know, different noise structure, different patterns and so on. And so better simulation. I'm not talking about cosmology, also better simulation of the data, better simulation of the training data. If Massimo wants to add something.
Well, yes, I agree with Pepe. Essentially, simulations are very useful in order to prepare the machinery, your tools, your software methods that that you want to use to explore the real data. Especially now with big data generation of large instruments from astronomy, it is impossible to not be prepared with simulation when the real data arrive, because when real data arrive, you don't have anything, you don't know exactly how to treat, how to handle the data. You probably will never be able to perform any kind of science investigation. But just it, from a quantitative point of view, are useful, not at all.
But regarding simulations, then when you are doing the simulation for unexplored parts, okay, you have to ensure that your simulation do reproduce what are the real observations. Because I have seen
If it is unexplored, what do you know what
when
the
you
area
get
of
the data
observation?
later, but
Yeah.
I've seen people training networks on
Yeah.
models to estimate physical parameters of
Yeah.
events and then apply those to data. And when I asked them, do your simulations reproduce the data, they couldn't answer me.
I
So,
think we
I mean,
we read the same work.
I don't know. I mean, the simulations are right, but then they must
Yeah.
have a good. I
Exactly.
think that what you mean by good simulation, better use
Yeah.
simulation, every simulation that actually. are
Obviously,
realistic,
yes.
because
Sorry,
otherwise-
I hope that was clear. They must be as close as possible to the real data, because otherwise, basically, your machine learning algorithm just goes nuts. Yeah, yeah. Why it's better to specify. You are absolutely right. So it's a wonderful task.
Other questions? Okay, thank you. Thanks again.
Thank you very much.
Giuseppe.